Hey everybody. Today we're doing approximate integration, this time using the trapezoid rule. So we're trying to get approximate values for definite integrals, particularly in cases where we can't use the second fundamental theorem of calculus. Here's the formula for the trapezoid rule. It's kind of a mess. We're going to want to go through the geometry of it a little bit to get some intuition, and then we'll do a full example. So remember that a definite integral is first and foremost interpreted as an area under a curve. So that trapezoid rule formula is going to come from trying to approximate this area in order to approximate that integral. We're going to divide the interval of integration, in this case from 0 to 6, into a bunch of equal pieces, n equal pieces. I'm going to show n equals 3. So if the interval is 6 units long and we divide it into 3 pieces, each one is going to have a width of 2. We'll call that value delta x. And then for each of those subintervals, 0 to 2, 2 to 4, and 4 to 6, I'm going to draw a trapezoid under the curve, like so. And then we're going to compute the areas of those trapezoids, add them all up, and that's going to approximate the integral, approximate the area under the curve. So we got to talk about the areas of trapezoids. The formula is 1/2 h b1 plus b2, where b1 and b2 are the parallel sides, in this case the vertical sides, and h is the distance between those parallel sides. So h stands for height, but here we've got it labeled left, right to go along with our picture for the definite integral. We're going to want to apply this for every subinterval on our graph, for every one of those trapezoids we drew. So let's do it. Here's that picture we had before. We've got 3 trapezoids. The one on the right has a base on the right of 0, so it degenerates into a triangle, but the formula works exactly the same. So again, the bases are going to be the values of the functions, the value of the function at the left endpoint and the right endpoint of each subinterval. Notice that h is always going to be the same. It's going to be delta x. In this picture, it's going to be 2. So we're going to approximate the integral from 0 to 6 f of x dx with those 3 trapezoids, 1/2 h b1 plus b2 3 times. So for example, in that first one, it's 1/2 delta x f of 0 plus f of 2. Let's simplify that formula a little bit rather than just plugging in, because I think it'll be enlightening to do so. Notice that they all have factors of 1/2 delta x. Let's pull those out. We've got 1 f of 0, 2 f of 2's, 2 f of 4's, and 1 f of 6. So the leftmost and rightmost endpoints, 0 and 6, are each represented once, and the other endpoints of the subintervals are each in there twice. So if you think back to that original formula for the trapezoid rule, here we're seeing where it comes from. Here's the sketch one more time. Here's the formula that goes with it. I think that you can now see the left endpoint and the right endpoint, f of a and f of b, and then twice all of the other endpoints for those other subintervals. Each term in that sum is going to represent an area of one of those trapezoids. Let's do a full example from start to finish. Integral from 0 to 2, 3x squared minus 15 over x squared minus 9. We want to use 5 trapezoids. Here's a picture. We're going from 0 to 2, so I've shaded the region underneath this graph between x equals 0 and x equals 2. So the width of that interval is 2. I divide it into 5 pieces, and I get delta x equals 0.4. So let's actually apply the trapezoid rule. Delta x is 0.4, so I'll plug that in. F of a is going to be f of the leftmost endpoint, f of 0. That only shows up once. And then I move over by the width of the interval, 0.4, plug that into f, and double it. I've got 2 bases with that value. Move over by 0.4 again, double it when I plug it into f, and so on until I get to the rightmost endpoint, b, which is 2. I plug that into the function and I don't double it. Okay, so now I actually need to take those values, 0, 0.4, 0.8, and so on, and actually put them into the function, get some numbers. Little help from a calculator, and I get 2.7559. The actual value of this integral, if you do it by hand using the fundamental theorem of calculus or using a computer algebraic system, is 2.7811. So even just with n equals 5 trapezoids, we're doing pretty well.